Hello and welcome back to Data Science with R for Social Scientists. In this session, I want to discuss data frames, tibbles, and tidy data. Most importantly though, I want to discuss how to tidy data. When you think back on the diagram about data science that we saw in the first session, we are now in the part that is highlighted in blue here. We've already talked about importing data, but today we want to focus on how to tidy it and how to do the first transformation that gets our raw data into a suitable form to start visualizing using the tools that we've picked up in the last few sessions. So now that we are back in our studio, I already created a new R Markdown file. And before we talk about tibbles, I want to start talking about a few other data types that are available in R. So to get started, we already talked about simple objects. Let's call a new object X. And what we've already done was to create a vector, and vectors are the simplest data structure that we have in R. They're simply a one-dimensional sequence of values, and those values have to have the same data type. So what I created here now is the most simple form of a vector. It only has the length of 1 and it has only one kind of data, which is numeric data in this case. We can look at the length of this object with the command length, and we can see that it is 1 element long. What we can also do is to store several values in this one object by using the C or concatenate function. And what we can do here is we separate the individual values with a comma, and what we can do now is we can store a few different values here. And when we do this, then the length will accordingly be 5. What we can also try is to store a different value in here. Let's say we want to store a character value in here. Let's call this 6 and let's see what happens. So we still have a vector with a length of 6, but even though most of the values in this object are numeric values, we can see that in the environment viewer up here, this is now a character object. So how can we find out what kind of object this is? In R, the different types of objects are called class, and we can use the class command to find out more about the object X. And as you can see here now, the object has the class character. This is interesting because of two reasons. First, character is really more a data type and not so much a class, but atomic vectors don't really come with a specific class. They are simply the class whatever data type is stored in them. And then secondly, most of the values in this object are numeric values. So why did R resort to calling this a character vector? The reason is because of the one character object in this vector. And what you need to know is that R coerces or changes the data type according to a certain hierarchy. On the lowest rank of the hierarchy are integer values, because even though you can store an integer in a numeric value, so you can add a 0.0 to every integer even though it doesn't add any information, you can't do it the other way around. You can't express 1.5 as an integer. With the same logic, you can't express a numeric value as a character. What's done instead is to convert it to simply put these quotation marks around it, and from now on, all of the numeric values are character values. Let's restore our first object here, which consisted only of numeric values. And let's copy this over so we can compare the two. And when we check out the class now, we can see that it is numeric. You won't see a mention of the vector class here because this is not a formal class. It simply means that this is neither a list or a data frame. So let's also have a quick look at lists, and I make a new object called xList. And what I can do here now is I can store actually the two vectors that I created before. So what do you think is the length of this list? It's actually 2, because a list is not a flat object. It actually has a hierarchy, and we can see this when we print the list object. We can see that there's a first element in here which itself stores a couple of different elements, which are the numbers here, and then we have a second element in this list which stores the values which were in the Y object before. When you look at the class, we will see it has a new class now. It's not called numeric or character anymore. It is called list. And what we can do is we can subset the list to get one of the objects back that we created. So let's say we want the first element. And what we get here now is again our vector with 5 numbers. And we can see that this is class numeric. So the class list can hold values of different data types. It can hold character elements and it can hold numeric elements. However, what you can't do when you print this once again is to have character and numeric values along each other. So inside one element of the list, which is displayed here under the 1 in dual square brackets, is one element, and in this element all values need to have the same data type, just as in the flat vectors here. Now, as I said in one of the last sessions, easiest way to look at an object in R is the view command. However, for both of these new data types, this doesn't really make a ton of sense. So if we try to view at X here, what it will do is to open this somewhat weird representation of the flat vector, which looks a little bit like a spreadsheet, but the values are stored only in this field here, and then we have a type description. So I think it is somewhat useful. Double in this case simply means numeric, and the 5 in brackets means that it is of length 5. But this representation isn't particularly useful. The same is true for the list object. What we get here is the individual elements of that list underneath each other, and again, Vue is doing its best to display the data in a useful way, but basically if you imagine this to be real data, you would have a hard time to see which of the values belongs to the same observation, since the two variables are displayed underneath each other and you don't really see which two values belong to the same case. So this brings me to the most important class that we are using, which is the data frame. There are 2 ways to create a data frame, and I'm just calling this new object df here. And when you use the data frame command here, what you can do is you can input the 2 vectors that we created earlier. When you run this now, R complains arguments imply differing number of rows. This is because a data frame is always rectangular, and R doesn't know how to bring this into a rectangular form, since X has 5 elements and Y has 6. So what we can do here is we can add a sixth element, or let's call this an A, since we didn't really have one before. And when we create this now, even though it is basically the same as the list, you will see that we have a couple more information. So first of all, it is displayed as an actual table here, where the two vectors that we put into our data frame are columns now, and the columns also have names. In the data frame command, you can also explicitly name these columns. So we could say X and Y here, and it would do the same, since if there are no names provided, it will simply take the name of the vectors that you put into the data frame. When we print this data frame now, you can see that the representation in R Markdown looks pretty fine. We can also print it in the console to see what the printing of the original data frame looks like. And you can see that it is actually not that bad. However, if we print the empty cars data set, which is built into R, for example, you can see that it is already a little bit harder to grasp what's in the data here, since we have one column here which doesn't have a column name, so we're not really sure what this column is. And it is quite long, even though there's a rather limited amount of cars in the empty cars data set. We already have to scroll quite a bit to see anything here. But let's say we want to look at, for example, the crim tab data, which is also built into R. Then we can see that it gets really messy because that data set has too many columns. And what R does here is to display them anyway, to display the first 100 values, and to simply break into a new line once there are too many different columns to display. And honestly, this is the biggest difference between tibbles and data frames. So it's not really that important which one you use if you want to use simple data sets. The only time where I really struggled with data frames is when I use text data, when I have one vector with a couple of hundred words in each element in a data frame. And so this breaking into a new line gets really, really messy. And sometimes when I have a couple of thousands or 10,000s of lines in a data frame with text, then R can even completely crash because it can't handle printing a simple data frame. So when we're using the tidyverse, it makes sense to use tibbles instead, and you can create them in pretty much the same way. So we use the tibble command, and this is already provided in the tidyverse package, so we don't need to load any extra package. And when you print this vector now, you can see that one, we get more information. So we have 6 rows here and 2 columns. We get the information what type each of the columns has. So double, as I said, is a numeric vector, and character, as I said, is a character vector. What's still true here is that it behaves similar to a list, that inside of one column you can only have one data type. Now, the book also tells us about the tibble command, and this is sometimes useful if you want to input data directly in your script. And the way this works is in the first line you provide column names. So let's just recreate our df2 here. So what's happened now is that tibble actually doesn't want to simply coerce the y column to a character, Instead, it complains that it doesn't know how to combine these two, which makes sense. So we have to do this ourselves, and it is a nice safeguard because before what happened was that simply the whole vector was converted to a character, and instead we get an error now which tells us that if we really want a character column here, we need to name it explicitly. So here we go. Now we created 2 tibbles, and again it displays our dataset in a really nice way, which is arguably not that different from the original printing. Tibble only shines where the regular data frame has problems. So if we convert the crim tab dataset to a tibble, and in order to do that, we have to tell tibble to repair the names because the crim tab dataset apparently comes with broken names. It's not really important why this is the case right now. Just wanted to show you that the representation is a lot nicer now. The book also shows how you can customize the printing of a tibble. So let's go ahead and do this. You use the print command, and then you can say that you want, for example, the first 20 rows instead of the first 10, which is the default. And here we go. Now you get the first 20 rows. But again, since we're using our Markdown anyway, this is not hugely important because our Markdown comes with its own object viewer. And as you can see here, it's even a lot more powerful since you can go through all of the different rows, and it simply has this menu at the bottom here, which is really helpful. Now we should also quickly cover how you subset data in R, so how you can get individual cells, for example, in a table, or how you can get individual elements. So let's say we wanted to have the third element from X, then you can do this by using the square brackets here, and if you want the third element, you just put a 3 in here, and there you go, it displays you the third element. For lists, you have to use 2 square brackets, and to get the second element here, I put in a 2, and this displays the first vector which we stored in our list. If we wanted the third element from here, we would have to use another pair of square brackets to get to the next higher level of the hierarchy in the list. As you can see, this is already getting a little bit confusing, but it's just to get you covered on the basics of R. Mostly we will be working with data frames, and this is mainly due because the entire tidyverse is constructed around the ideas of using data frames as input as well as output. But anyway, let's use the traditional way of subsetting a data frame and compare this to how you can do it in the tidyverse. So here again, you use square brackets, and when we look at this data frame now, and let's say you wanted to have the 3 in the Y column, then what you need to do is you can first need to provide the row. So the row is 3 here, and then you need to provide the number or the name of the column, which is 2 or Y in this case. So let's try this. We want the third row and then the second column. And again, we get the 3 as expected. Or, as I said, you can use the name of the column as well. And this has the same effect. Let's make a note of this. In the tidyverse, you do things differently. You can also use the traditional subsetting method, but in my opinion, it's a much better idea to use the deployer verbs that we've learned. So let's say you wanted the third row, Then let's filter. And now you need the dplyr command row number. And we want the third row. This might seem a little too complicated, but I would also argue that in most cases you don't want to get specifically the third row. What you rather want to have is a certain value. So we could also filter for the value here, and that would probably be a better idea. So let's say we wanted to have the x value 3. So there you go, it only displayed the third row anyway. But let's keep with this example, and then let's say I only want the value from the y column, and you already know how to do this. You select, and then you select y, and here we go, we have a single value here. However, as I said, a part of the tidyverse is that you always input a data frame and you always get a data frame out of it. The only exception is if you want to specifically get a vector now, you can use the pull function to pull out a single value. So as I said, I mainly explained this because it covers some basics of R, and some people, of course, still use the traditional way of subsetting data frames, and of course you need the traditional way to subset individual vectors. But I think that the R community has slowly transitioned to the tidyverse way of doing things because it is more explicit and it is closer to the actual English language, where you have these verbs such as filter and select, and not just a programming language where you have to know what the brackets mean. And especially with lists, it is easy to forget how specifically you can draw out one of the elements here. And when you have more complicated filter and select combinations, those are rather hard to display in the traditional way of selecting and subsetting data frames and vectors. So then let's get to the main topic of today's session, which is tidy data. And Hedley Wickham borrows from Leo Tolstoy here when he says that tidy data sets are all alike, but every messy data set is messy in its own way. I'm using again some artwork from Alison Horst here to explain what exactly tidy data is. And let's get started with another quote from Hedley Wickham. Tidy data is a standard way of mapping the meaning of a dataset to its structure. This is extremely powerful and not just a strange quirk that some data scientists have, although you will find some data scientists who absolutely insist of using only tidy data, even when it only makes limited sense. So what exactly is tidy data? There are 3 principles, and as explained in the book, they are closely interlinked, and one of them can't really be true while another one is false. So the first principle is each variable forms a column, then each observation forms a row, and each cell is a single measurement. If you look at the right-hand side of the slide, there's a simple representation of a tidy table. And as you can see here, we have 3 different variables which are stored in 3 columns: ID, name, and color. And then we have 6 observations which are stored in 6 rows, and we have 1 value in each of the cells. So it's super easy to quickly grasp the different observations here. They are in the same row, so you will immediately know that ID3, the name of the observation is cat and the color is orange. So as said, all tidy data sets are pretty much the same. The columns are variables and the rows are observations, but every data set is messy in its own way. So when we look at the first guy here, my columns are values and my rows are variables. This might not seem super important to you, but when you think about what we just learned, that in R, in every column, you can only store one data type, you quickly understand that it is really problematic to have a data frame where the columns are really observations. Because, I mean, one observation could be an orange cat, and that cat was born in 2015. We now can't store the 2015 as a numeric value anymore. We have to store it as a character value because the other two values in that column are already character. Looking to the next guy, I have variables in columns and in rows. This is, again, super problematic because sometimes when you want to filter for a specific value in a variable, you can use filter, and then at other times you actually have to use select, because what you want to do is you want to filter out certain columns. Because in this guy, some of the columns are actually observations, and at other times they are variables. So we get confused really quickly using our tools. Then the next guy, I have multiple variables in a single column. This is of course problematic when you want to do something like mutate, where you want to create a new column based on, for example, multiplication of two other columns. And when then one of these columns contains multiple values, you can't do your multiplication anymore. You first have to somehow separate the values from this one column. And then the last guy here, I've seen him over and over in the wild. I don't even know what my deal is. Yeah, I often think that when I get data sets that someone who has no idea about data science produced, and of course, I mean, this is fine. This is not the job of people who enter data, but we have to deal with it, and it sometimes gets a bit frustrating. So why do we insist on tidy data? It's, as I said, not just a question of personal taste. It's really because we then can build our tools around one specific way of representing data, which is the tidy way. And if you look at the two workbenches here, you can see we have a few very clearly marked tools which can deal with tidy data. And then on the other side, we have the untidy data workbench. There are a couple of R packages which deal with really quirky data, but it is often extremely frustrating and annoying to learn them because they work in such a very different way. And if you look at that monster at the bottom on the right here, he's really breaking a sweat because there's no easy way of understanding how these tools work. So especially when you want to work with any of the tools in the tidyverse, you need tidy data, but in general, it's easier to build tools for tidy data, and once you get the hang of it, you're much quicker in learning these tools. So let's get started with a couple of examples. Just to make it even more explicit than before, we have table 1 here from the tidyr package, which is part of the tidyverse and is especially useful when you get messy data that you want to tidy up. So table 1 here, we can see we have 4 variables: country, year, cases, and population. Those are stored in the columns. And then we have a couple observations, and here the observation is really Afghanistan in 1999. So we don't have an ID here. We probably would need to create our own ID. We can distinguish the first 2 observations by saying, okay, this is not just Afghanistan, but Afghanistan in 1999 and in 2000. But other than that, table 1 is pretty clear and it is definitely tidy. Then looking at table 2, also from the tidyr package, we see that we have country, year, and then we have the 2 variables cases and population stored over 2 different columns. So we have one column which is called type, which marks if a row displays the number of cases or the number of population, and then you have the actual value in the count column. You can already imagine that this is much harder to, for example, visualize, because if you wanted to plot the cases, you would first need to filter all the rows that contain case numbers. And then if you wanted to plot population, you would filter to only keep the rows in the data which speak to population. And then if you wanted to plot both, well, I'm not really sure how to do it without first tidying this table up. Moving over to table 3, we still are dealing with the same variables, but this time, while we have country and year in columns, we have a column called rate. And in this rate we have again the cases and the population separated by a forward slash. So let's think again of the 3 rules of tidy data. Each observation forms a row. The second one, this is true here, but where it gets problematic are the first and the third. So each variable forms a column. Not really. We have really 2 variables here, but okay, we can say this is one variable, this is rate, but then the last clearly broken. Each cell is a single measurement. Well, actually no, each cell has 2 measurements. It has the cases and the population. Then next we have the 4 variables spread into 2 tables, table 4a and table 4b. Table 4a contains the cases and it has 1999 and 2000 as columns. So really the variables here would be the individual years, and I can kind of see that some people would argue that this actually makes sense, but on the other hand, if you want a second actual variable here like population, you would need to create a different table. And then how do you visualize this? At least with ggplot it would be really tricky because you can always just have one dataset as an input. And then finally table 5. It's similar to table 3, but not only does it store 2 variables in one column, it also stores 1 variable over 2 columns. So the year number is split into century and year, which of course can sometimes make sense, but I would argue that this is probably harder for plotting, and if you needed just a year number, for example, in a plot, then it would probably be easier to create another column called year short or something like this. So let's go back over to R. I put the 4 tables from the tidyr package in here, and since tidyr is automatically loaded with the tidyverse package, they are already present in our environment. As I said, table 1 is fine. We don't actually have to do anything with it. I'm just leaving it in here. It is already tidy. Then let's get to table 2, and here we have to use the first command from tidyr, which is called pivot wider. In the book, this is called spread, because some while ago the developers of the tidyr package gave in to constant criticism of the gather and spread commands and replaced them with a much easier to understand pivot wider and pivot longer, which we will learn in a second. So out there are currently a few people who still like spread and gather, and then the majority of people switched over to pivot wider and pivot longer. So what pivot wider does, and we can look at the help here of course, is to increase the number of columns and decrease the number of rows. So let's see, we want to pivot over the cases and populations into new columns, and we do this with the argument names from, and then without quotation marks we point it to type. And then we want to pivot over the values into those 2 new columns as the new values. So we tell pivot wider to take the values from count. And once we do this, you will notice that table 2 now looks exactly like table 1 and is actually tidy. So then let's look at table 3. Here we need another command from tidyr, which is helpfully called separate. And what you do in separate, as the pop-up shows you, or even better, let's look at the help. Given either a regular expression or a vector of character position, separate turns a single character column into multiple columns. So then what we want to do is we want to select which columns we want to separate, which is the rate column. We want to separate it into, and here we have to use character vectors, into cases and another column called population. And then we want to separate it using the /. And here we go. Again, we have our nice, tidy data frame. When you look at the help file here, you see that the value for separate is actually much more complicated, but we can try it with this one as well. And it basically does the same thing. This is a so-called regular expression, and we will learn about regular expressions when talking about strings, but basically it's its own little programming language that is present in almost any other programming language that exists today, because it helps to represent a certain sequence of characters in a high-level way, so it essentially functions as a search. What this here tells us is to look for alphanumerical values and to use those as the separator, but then the second square brackets with the power sign explains that actually we want the opposite. We want everything that is not an alphanumerical character, and then the plus at the end means that even if there are more than one character which is not numerical or an alphabetic sign like ABC and so on, then use this as the spread. But for now, let's keep it simple. Let's use the actual value that is used in table 3 to spread the rate into cases and population. And then, of course, if you want the rate back, it is super easy to do this with mutate. You simply create a new column called rate, and you create it by dividing cases by population. Or it is almost that simple. Because if you look again at this table, you will see that cases here is still a character vector, population is still a character vector. So what we could do is to convert them on the spot. And there we go. Now we have the rate, which is numeric, as you can see by the abbreviation for double, which simply means numeric. You could also create two new columns, or you could replace the two columns, cases and population, by saving this. So let's do this as well, even though it is sort of a duplication, but let's override cases with the numeric representation of cases. And let's do the same for population. So here we go. Now we have again the same table as before, but with the added rate, which is now actually calculated and not just a visual representation. So let's move on to table 4a and 4b. These are actually the most complicated ones so far, but every single one of them is not that not that complicated. We simply use pivot longer, which is the counterpart to pivot wider. And here we need, let's look it up, we need to specify which columns we want to use. In this case, we want to use the column 1999 and the column 2000. Because there's a number at the beginning, we have again to use those quotation mark like signs here. And then we want the names, so this means the names of the columns, to go into a new column which we'll call year. And then we want the values to go into a new column called cases. And then we can copy this over and do the same with table 4b, except this time we call the value population. And again, we have essentially the same as table 1, but it is still spread over 2 different tables. We will learn in one of the next sessions how to actually combine these 2 tables so that we have, again, the whole information in one single table. And then table 5, as I said, combines 2 of the problems that we've seen. And then table 5 combines one of the problems that we've seen before, namely that rate really contains 2 variables, with a new one, which is that the year is now spread between different columns. So let's first copy over the separate part to take care of that. And then next we need a command which is called unite. And here in unite you have to watch out because the call argument means something different here. It's actually the name of the new column that you want to create. So let's name this new column year, and then we can supply the old columns that we want to use for the combination. These are century, and year. And then finally, when we keep the default, which is an underscore, the new column will have an underscore between the values from each of the columns that we combine here. So to get an actual useful year number, we just remove this and supply an empty character string to separate, and we have the year here. And then all we need to do is to mutate again and convert the year to a numeric and do the same for cases. And then finally, population. And then here we go. We're back at table 1. And now that we warmed up with tidyr a bit, let's look at 2 short case studies. You can also work through the case study in the book, but I wanted to show you 2 different ones, which I also already highlighted in the announcement. And I want to first look at the COVID data by Johns Hopkins. And I already opened their GitHub repository here. So that's the COVID-19 data repository by the Center for Systems Science and Engineering at Johns Hopkins University. And this is basically the COVID data from all around the world. You can see here that they include US states and then many different countries. As far as I know, this is almost a complete data set for the entire world. And as I said, it's updated daily, so the last update was 4 hours ago. And when I now go to this folder here, you can see that we have some time series data. And what we have here is confirmed cases, recovered, and deaths, unfortunately. So let's look at the cases here. This is again a CSV file, and as I told you before, you have to click on the download button here to actually see this. This is of course a CSV file, so this is impossible to look at. So let's quickly save this in our data science folder. And now that is in the folder here, I can open it with, for example, only Office. This should also work with Microsoft Office, of course. Here I can set the delimiter, which is comma in this case. And here you go, you can see that this is actually possible to open this directly in a spreadsheet software like only Office or MS Excel. But we don't really need to do this. We can directly copy the link. And then inside of R, I can give this a new name. Let's call this COVID data. And then as before, we simply choose the RIO package, import, and then I put the name in here. And there we go. We can look at it. And now we can check, is this actually a tidy data set? Let's look at the slide by Alison Horst again. So each variable forms a column here. We can see that province and state, the first variable is inside a column, country and region is inside the column, and then latitude and longitude of this region is also in a column. But then next we have the 21st of January 2020. I wouldn't say this is really a variable. You could again argue that it might be, but I would say that this is rather an observation. So we check cases. The whole data frame is confirmed cases. So I would rather say that the 22nd here is an observation. So this data frame doesn't pass the first rule. It also doesn't pass the second rule, since one of the observations is inside of a column and each cell is a single measurement. At least this one seems to be true, except of course these are observations here, so the measurements for this observation go down this column here. So how can we change this? Let's first play a bit with it and then copy the code to our actual ingestion command. Again, we need the pivot longer command. And what we want to do here is we want to collect all columns that start with a number. So the number is 1, 2, etc. So we want to select the columns that start with a number. Let's have a look at the help file here, if this is something we can do. It tells us here tidy select. And we've basically already seen tidy select in the select function. And as you can see here, we have a couple of options selecting a range of consecutive variables. So what we could do is we could select this first and then check what the final variable is, taking complement of a set of variables. So this is basically, we can name a couple of variables and then take the opposite of them. So it would be an option to tell pivot longer that we don't want the province, country, latitude, and longitude, but we want all of the others. We also have and or again, and we have the C for combining. We also have a couple of helper functions that I haven't mentioned before. For example, we could use matches. This uses regular expressions, and I think I want to go with this one. So matches uses a match, and we will discuss regular expressions in the very last session. But just to name one useful regular expression here, we can start with the power sign, which indicates that the string that we are looking for should start at the beginning of the character vector. So here, that means the start is the 1 here. So we want a start followed by a numeric character. So this is D. And then we basically don't care about the rest. So this should be good enough. Everything that starts with a number is included here. So then let's return to the help for pivot longer. Then we want to specify the names to argument. So what will happen to the names of the columns here? And we want to put this into the new column date. And then the other thing that we want to do is we want to specify what to do with the values, and we put those into a new column called cases. And I want to directly look at this, so let's pipe this into the view command. And there we go. Now we have one observation per row. So we have Afghanistan and the date, and then the number of cases here, which is 0. So this already worked pretty well. Sometimes you have to use some of the other commands, but usually what I do is to simply use columns, names to, and values to. What we could also test is if the other approach that I named, which is to select columns by specifying which ones not to use, would work here. So let's try this. So we don't want to use the following columns, and I'm using the autocomplete feature here to select the first ones because they have these tricky quotation mark like signs around them. So what I like to do is to simply type the name of the dataset and then use the $sign and then use the autocompletion to get to the variable that I'm looking at. And then it was long and let. And when we try this now, same thing. So I'm leaving both options here. Leaving this as a comment, and then I'm reverting back to the regular expression here. And again, we will learn in the last session how these regular expressions work exactly, and I will give you some hints on where to find help about them. But here we go. When I do this now, we have a nice tidy data set directly downloaded from GitHub. So when I rerun this command tomorrow, the new data will have been automatically added because the people at the repository updated the dataset with the newest numbers. So what can I do with this now? We can directly get into plotting. We can use the COVID-19 dataset, and probably we want to select only a couple of countries because there are so many in here. So let's see. I want the numbers for Germany. Yeah, so I have to select country region Germany. or I mean I say select, but what I really want is to filter. And I want to select a couple ones, so let's use in Germany, and of course this has to go into quotation marks. And then maybe let's take France. Yeah, France is also in here. And this should be enough for now. And then we want to map the aesthetics. So the x-axis should be the date. And the y-axis should be cases. And then we want a line plot. Okay, this is really confusing. And the reason is because we haven't really done anything with the date variable yet. So since ggplot doesn't know what the date variable is, it sees this simply as a character vector. It doesn't know how to order it, and it orders this alphabetically, which is of course super confusing. So it takes the 1st of January 2022 first, then it goes to the 1st of October 2021. Really confusing. So what we want to do instead is to tidy this a bit further. So basically what happened here is that data is stored in the wrong type. So it's not stored as a date, but instead it is stored as a character vector. And we're using a new package for this, which we will also learn in one of the later sessions, which is the lubridate package. And the lubridate package can basically convert dates really easily into the internal date format, and it has specified functions for this. So it only needs to know which of these numbers here is the day, since this is stored in the American time format. The day is in the middle. Then the package wants to know what's the month. The month is the first number here, and the year is the last one here. So we need to use the function m for month, d for day, and y for year. And as you see, this is a valid function here. And when we now put in the date column, this should work. And when I look over here at date, it now confirms that this is in the date format. So let's open this and let's sort it again. You can see now we have the different countries here, and we have all of the observations that were made on the 21st of January 2022. It automatically changed to the international date format, which is the year comes first, then the month, and last the day. So let's try this again. Let's plot this. And yeah, as you can see here, we now have a plot that makes a lot more sense, but the problem is we still only have all the cases. We haven't differentiated between the two countries yet, so we can do this with color. And then we take the country region variable. And this still looks pretty weird, but I found out what the problem was. So when we look at the data and we only display France here, then you can see that France has a couple of different provinces. But what we want is the one which doesn't display a province, which is mainland France. So let's add another filter. and we only want the empty province state. Needs to be a / here. And here we go, now we have a nice line plot. You simply couldn't have done this without first tidying the data. And then a second example that I have here is a data set from the World Bank about internet penetration. So we have the number of individuals using the internet in % of population. And this is one of the worst files that I've worked with in my PhD because it starts with a few rows which are neither observations nor variables. It's simply additional data on the data set. And then again, we have the observations here in columns instead of rows. So this is a bit tricky. Don't download the data from the World Bank directly. There is a package for this called WB Stats, and it at least gets rid of these annoying first lines here. But I think the tidy is still not really data that you get from there. And anyway, maybe you found your file on a different website and it looks like this. So let's see how we can deal with such a file. So first, let's read it into R with RIO again. And this time, since we have a local file, we can use the opportunity to talk about file paths again. I place this into the data folder in my project directory. So we start the path with a point to indicate we are starting from the current directory. And then we enter data. And then we want a file called toAPI. Oh. So I can press the 2 and then I can press tab to autocomplete the file name. And when I now read this into R, it doesn't look too bad. It automatically skipped the first couple of lines and it looks like it mostly read in the data correctly. So let's scroll over and yeah, we can see the columns over here even seem to be numeric already. Let's check this. Yeah, they are identified as integers. So this is already pretty good. But as you can see on the top here, the column names are completely botched. So we need a couple of additional arguments. Let's look at the help file. And when we scroll down in the help to import, you can see that comma separated files. So this is what we have here, a .csv file. To import this, the package is using the fread command under the hood. And here in fread, you can see there are just tons of arguments. This is a really confusing help page, but two things that we want from here are skip. And skip means start on the first line is the default, or start at a later line. So when we look here, it would usually start on this, but since fread is already pretty smart, it knows that this is basically an empty line with just some information at the beginning. Here, second one is completely empty. Third one, we again have some metadata, which is not that interesting. Fourth one, empty again. So we want to skip the first 4 rows. And then secondly, what we are looking for is header. Does the first data line contain column names? This is indeed the case. When you look at the data again, you can see country name, country code, indicator name. These are actually the column names. So we simply set header to true, which indicates that true is applied. Any empty column names are given default names. All right, so let's try this. Yeah, this looks pretty good. And I mean, of course, the NA values here seem a little bit strange, but it makes sense once you think about what kind of data we have here. We have internet usage, and in 1982 there were no people using the internet in Burundi, and probably also almost nowhere else, because the internet, this was even before the days of World Wide Web, so there were really very few people actually using the internet. Okay, so let's tidy this up once again. Again, we want to pivot these columns over into rows. And when I look at the other those two columns here, when I sort them, yeah, they are constant, so there's no information in here. So what we could do to make this a little bit easier is to first deselect them. So this is done using minus and then a C. And I want to get rid of indicator. Let's use the little trick here again. Indicator name. And indicator code. And then country name and country code. Okay, I mean, we can keep the country code, but I would prefer to rename them so we don't have to use these weird signs here. So let's rename country name to simply country. And then country code we can rename to country code, but with an underscore instead of white space, so we don't have to use these weird signs around the column names. All right, this looks pretty good. So now we can pivot our data. We want to pivot it longer, and the columns we want to select is everything except country and country code. And then we want to transfer our names into a new column called year. And the values should go into usage. Okay, perfect. This looks good. Let's check it with the view command. So we have a 0 here, and yeah, Bahrain in 2019 there was 99.7% internet usage. So this checks out. And again, once we are happy with the tidying, we can directly copy this to the command that imports the data, so we don't have an unnecessary object in our environment. We now have the nice and tidy data frame here called WP Internet. And the only thing I need to check, yeah, year is still a character. So this would again probably cause some issues with ggplot. It doesn't look like it, but just to be safe, let's still convert the year into a proper format. We could go with date again, but I think in this case numeric should be fine. Yeah, NA is introduced by coercion. That's fine. Some of the years can be converted to a numeric vector. But as you can see, for most of them it worked. Let's check out the cases by scrolling down. Okay. I wonder what these were before. Let's copy the name of the Sudan and try this without the mutating. How does the data look before? Okay, so we had one called V66 here. And this is probably an additional empty column in the CSV file. So what we could also do is to include it up here in the ones that get deselected. And there we go, we get rid of the error message. Okay, and now again it is super easy to plot this. Let's put this directly into ggplot. And again, let's map the year to the x-axis and usage to the y-axis. And we can use color to indicate the country. Let's take geom_line again. Misspelled the name of ggplot. All right, and this is a huge mess because I selected all of the countries in this data set, which is far too much. So let's try to filter out a few ones. Let's try Germany again. Can include Israel just because I can see it here. Let's go with Kuwait. And I mean, the internet was developed in the United States, so be interested to see this as a comparison to the others. And yeah, it's just called United States here. So let's add this to the mix and let's see how this looks now. There we go, pretty nice. So we have a lot of NAs in the beginning here. We could probably filter them out to get the plot more focused, but I'm gonna leave you with this, and you can enhance the plot if you find it interesting and want to use it somewhere. And with this, I leave you for today. I will again copy a few exercises in here. We won't use all from the book this time, but if you want to practice a bit further, you can do so with a couple of selected exercises. And with that, thank you for staying on the entire time, and I see you in the next face-to-face session. Bye bye.